The hidden cost of efficiency. Understanding algorithm complexity in software systems in today's world of high-performance computing and cloud-based services. Understanding algorithm complexity has become critical for developing efficient software solutions. Developers often overlook that while an algorithm might seem correct, its performance characteristics can determine whether a system scales gracefully under load or fails catastrophically when handling larger datasets. This hidden cost of efficiency is particularly evident in modern web applications where millions of users interact simultaneously. The difference between O(n) and O(n) superscript 2 algorithms can mean the difference between a responsive user interface and unacceptable delays that drive away customers. Decoding time complexity notation. The Big O notation serves as a standardized way to describe how runtimes grow relative to input size. This mathematical representation abstracts away constants and lower-order terms, focusing solely on dominant factors affecting growth rate. To properly analyze time complexity, developers must first understand asymptotic behavior. As inputs approach infinity, certain patterns emerge that reveal the fundamental scalability limits of different approaches. Example: a linear search operation requires n comparisons in the worst case, resulting in O(n) time complexity. However, using binary search reduces this significantly to log2n operations, achieving O log n performance instead. O(1) constant time operations maintain consistent execution regardless of input size, such as array indexing or basic arithmetic calculations. O(log n) logarithmic complexity arises from divide and conquer strategies like binary search algorithms that reduce problem space by half at each step. O(n) linear time algorithms process data sequentially without significant optimization. Common in simple traversal tasks. O(n) log and frequently seen in advanced sorting algorithms like merge sort and quicksort, which combine recursive subdivision with linear merging phases. O(n) superscript 2 quadratic complexity becomes problematic at scale due to nested iteration structures commonly found in naive implementations of matrix multiplication or bubble sort. O(2 to the power of n exponential time problems are generally unsolvable for large inputs but still appear in combinatorial scenarios like subset generation, evaluating space complexity while time complexity measures computational effort. Space complexity quantifies memory requirements across different input sizes. Both dimensions need careful analysis when designing systems that handle big data workloads. Determining auxiliary space usage versus total space consumption helps distinguish between temporary memory needs and persistent storage demands. For example, a radix sort algorithm uses additional arrays proportional to the number of digits being sorted. Data structures and memory overhead. Choosing appropriate data structures heavily influences both time and space complexities. Hash tables offer average case constant lookup times at the expense of higher memory overhead compared to balanced trees. A linked list implementation typically consumes more memory than an array due to pointer indirection, although it provides better flexibility for dynamic resizing. This trade-off illustrates the importance of considering architectural decisions beyond pure algorithmic considerations. For instance, Python's built-in dictionary maintains amortized O(1) performance through clever hash table optimizations while managing memory allocation automatically behind the scenes. Similar principles apply to Java's hashmap implementation and other container classes. Analyzing practical algorithms. Real-world implementations often involve multiple interdependent components whose combined effects create complex runtime behaviors. Decomposing these interactions allows developers to isolate key performance bottlenecks effectively. Taking insertion sort as a case study reveals interesting properties, although theoretically worse than merge sort for large datasets. Its simplicity makes it more cache-friendly and potentially faster for small lists in practice. Case study insight. In embedded systems with strict real-time constraints, the predictable performance of simpler algorithms may outweigh theoretical improvements offered by more sophisticated alternatives. Bubble sort's simplicity makes it useful in educational contexts despite poor scalability. Insertion sort benefits from existing ordering within subarrays, making it efficient for nearly sorted data. Quicksort's optimal average performance comes with the risk of worst case O(n) superscript 2. Degenerate cases. Merge sort guarantees stable sorting with consistent performance but requires extra memory. Empirical benchmarking versus theoretical analysis. Theoretical models provide essential guidance, but practical evaluations remain crucial for accurate assessments. Factors like hardware architecture and caching mechanisms can dramatically alter observed performance. Profiling tools allow developers to measure actual execution times across varying input sizes, revealing discrepancies between ideal complexity predictions and real-world results. This empirical evidence guides informed decision-making during the development lifecycle. Performance characteristics across different architectures. Memory hierarchy design significantly impacts how well different algorithms perform. Cache-aware algorithms take advantage of spatial locality to minimize memory access latency. CPU pipelining and parallelism features affect instruction throughput differently based on algorithm structure. Branch prediction mechanisms favor code paths with regular control flow patterns rather than unpredictable jumps. These hardware-level characteristics make some theoretically superior algorithms less effective in practical deployment environments. Proper benchmarking accounts for these realities by testing on target platforms before final implementation decisions. Complexity trade-offs in system design. Designing efficient systems involves balancing competing objectives where optimizing one dimension often affects others. Engineers must consider multiple metrics including correctness, reliability, maintainability, and security alongside performance characteristics. In distributed systems, reducing message passing costs might lead to increased memory usage elsewhere in the network. Database query optimizers demonstrate this balance by choosing between index lookups and full table scans depending on current workload conditions. Microbenchmarks and performance regressions. Automated microbenchmarking suites help detect performance regressions early in development cycles. These tests measure isolated components against established baselines for consistency assurance. However, maintaining meaningful benchmarks requires careful calibration since changes in underlying libraries or compiler versions can artificially inflate or deflate measured values without actual functional degradation. Continuous integration pipelines integrate these checks automatically, ensuring that every new contribution adheres to predefined performance standards set by project guidelines. Emerging trends in algorithm optimization. Advances in quantum computing promise revolutionary breakthroughs in solving currently intractable problems, although practical deployments remain several years away from mainstream adoption. GPU acceleration leverages massive parallelism available on graphics cards to execute thousands of threads concurrently. This approach excels at data-intensive computations like matrix manipulations used in machine learning frameworks. Specialized hardware considerations. Hardware-specific optimizations can yield remarkable improvements. SIMD instructions enable processing multiple data elements simultaneously, drastically increasing throughput for vectorizable operations. FPGA-based accelerators offer configurable logic circuits tailored to particular workloads. Companies utilizing financial modeling applications benefit immensely from custom-built coprocessors optimized for their domain-specific needs. Such specialized architectures require corresponding modifications in algorithm design, emphasizing the growing need for interdisciplinary collaboration between software engineers and computer architects. Educational resources for mastering complexity concepts. Aspiring programmers should familiarize themselves with foundational materials covering formal methods, discrete mathematics, and computational theory to build robust analytical capabilities. Hands-on coding exercises complement theoretical knowledge by exposing students to concrete examples illustrating how different implementations translate into measurable performance differences. Online platforms offering interactive learning experiences help reinforce understanding through immediate feedback mechanisms that highlight areas requiring improvement. Practical tips for efficient coding practices. Writing clean, readable code forms the basis for sustainable maintenance and future enhancements. Clear variable names, modular functions, and documented assumptions aid long-term comprehension. Implementing profiling-guided optimizations ensures efforts target genuine bottlenecks rather than perceived issues. Monitoring tools identify hotspots deserving attention without guesswork. Avoiding premature optimization prevents unnecessary complications. Focus first on creating functional solutions before refining them for improved efficiency. Regular refactoring sessions keep codebases healthy by eliminating technical debt accumulated over successive iterations of development and modification. Collaborative code reviews facilitate cross-team knowledge sharing while catching potential inefficiencies earlier in the development pipeline. Common pitfalls to avoid newcomers frequently confuse algorithm selection criteria, leading to inefficient implementations even after grasping basic complexity principles. Recognizing these pitfalls enables proactive avoidance during development. Over-engineering solutions introduces unnecessary abstractions that complicate debugging without providing tangible benefits. Simpler, direct approaches usually suffice for initial prototypes and less extreme performance is required. Neglecting edge cases creates unreliable behavior for unusual input configurations. Comprehensive test coverage detects these weaknesses before they manifest in production environments. Poor version control practices hinder collaborative troubleshooting when unexpected regression appears. Maintaining clean commit histories simplifies identifying sources of performance deterioration. Inconsistent naming conventions contribute to confusion during code navigation and documentation creation. Adopting widely recognized style guides improves overall team productivity. Conclusion: understanding algorithm complexity is not merely an academic exercise, it directly impacts the viability and success of software projects in production environments. From basic programmatic tasks to intricate distributed systems, awareness of time and space requirements informs every engineering decision. By cultivating a deep appreciation for algorithmic efficiency through continuous learning and practical experimentation, developers can construct solutions that deliver exceptional performance while remaining adaptable to evolving technological landscapes and changing business requirements.